Okay, so let's take a look at question 4, part B from the 2011 scholarship paper. I just want to make the point that I made a bit of an error on the question 4, part A. Some of the calculations, everything is correct except for the final division, and there's a note or a comment for that video for question 4, part A. Basically, I was using a phone calculator instead of a regular calculator, so that's why those calculations are a little bit off. So I have a new calculator, just went and bought it to make sure I get these final calculations correct. Now this question is about the condition known as gout, which occurs when the concentration of uric acid, HUR, and urate ions, UR minus, in the blood becomes too high. Uric acid is a weak acid with a pKa of 5.4 at 37 degrees Celsius, which is internal body temperature. At 37 degrees Celsius, the solubility of sodium urate is 8 by 10 to the minus 3 moles per liter. And you know that's the solubility value because these units of moles per liter. And the solubility of uric acid is 5 by 10 to the minus 4 moles per liter. In blood serum, the concentration of sodium ions is 0.130 moles per liter. And blood serum, we're assuming we have a pH of 7.4 and body temperature of 37 degrees Celsius. So part 1 is calculate the maximum urate concentration at which sodium urate will not precipitate, and show by calculation that uric acid will not precipitate at this concentration either. So what we need to do here is look at the bit of chemistry that's taking place. So I've rewritten this stuff on a new page here. So we're looking at the possibility that this is happening inside of villus, which are those finger-like projections which are in your small intestine, and then we've blood vessels inside those little pieces of tissue. And inside the blood, we're talking about sodium urate, solid sodium urate, is breaking down into, or is in equilibrium or breaking down into its constituent ions, which are sodium plus ions and urate, UR minus ions. You're given a Ka for that, not a Ka, rather a Ks you have to work out. So get rid of that, swap those around, wrote them the wrong way. So you're given a Ka for the acid situation, but you need to work out a Ks for that situation there, because the question here is if the ionic product of equation 1, if the ionic product is greater than the Ks for sodium urate, then you will get precipitation. So this is the key idea here. So if the ionic product, the IP, is greater, so if the ionic product is greater than the Ks for sodium urate, then you get precipitation. So we need to work out the Ks at some point for sodium urate. We're also then, the urate ions can be in equilibrium with protons to form uric acid and water. So these two equations are interrelated, and this is what's happening inside the body at pH of 7.4 and the temperature of 37 degrees Celsius. The Ka you can work out from the pKa value. So the pKa value was 5.4. Again, I highly recommend having these questions printed out and in your hand as you watch this video, because that's what I'm doing right now. So the Ka works out to be 3.98 by 10 to the minus 6 for that acid dissociation. We can also assign a few other numbers as well. I'll just use a different color. This is the beauty of laying things out as equations. The concentration of sodium ions at pH of 7.4, you're given from your equation as from your question as being 0.130 moles per liter. So you can write that in there. Your concentration of sodium urate, because you're talking about its solubility at 37 degrees Celsius, is 8.00 by 10 to the minus 3 moles per liter. So you can write that there. And then you can also write down your concentration of H3O plus, the hydronium ions, because you can take 10 to the minus 7.4, which is the pH you're given. So 10 to the minus 7.4 gives you your concentration for down here, which is 3.98 by 10 to the minus 8 moles per liter. So you can write those numbers in, and then you can start to see what we're looking for. Well, we need to determine, first of all, the concentration of urate ions at this particular pH if we want to work out the concentration of the uric acid. And then from the uric acid, then, well, we'll be able to determine the calculation for the second part, which is uric acid, to determine will it precipitate at this concentration or not. So we have to do two separate calculations, and in both cases we're considering whether you get precipitation of either the uric acid or you get precipitation of the sodium urate. So let's take a look at equation number 1 here, the sodium urate situation. So let's just scroll on down here. Equation 1. So we're determining, from equation 1, we want to determine the concentration of our urate right here. And we know the Ks. The Ks is simply an expression of the concentration of sodium ions times the concentration of urate ions. It's one of the simplest types of Ks expressions you can write, because this is an AB type ionic solid, so just one ion of each constitutes the solid compound. So the Ks expression can also be said if is equal to Ks is equal to S squared, where we're saying S equals the solubility, particular solubility of the solid in this case, which is sodium urate, and at 37 degrees Celsius. So that's S is therefore equal to our 8.00 by 10 to the minus 3 moles per liter, which we just wrote over it in the equation. So the Ks then is equal to 8.00 by 10 to the minus 3. You square that number and you get a value for your Ks of 6.40 by 10 to the minus 5. So our Ks expression can be written up here, 6.40 by 10 to the minus 5. We now can use that Ks expression to work out a concentration of urate ions, because we also know the concentration of, so our Ks is equal to 6.40 by 10 to the minus 5. If we look at this expression for a second and rearrange it, Ks over the concentration of Na plus will give us our actual concentration of urate ions for this particular concentration of sodium, which is 0.130 moles per liter. Okay, and that works out to be a concentration of urate of 4.9 by 10 to the minus 4 moles per liter. Now, if we take a look at that, the Ks value is 6.40 by 10 to the minus 5, and therefore 4.9 by 10 to the minus 4 is a larger number. So that suggests that the urate ion would dominate. But we just want to back this answer up and work out from that concentration of urate ions what actual concentration of uric acid ions will we have, and if that concentration is greater than the Ks, then we will get precipitation. Okay, so for the second part now, we look at this second equation right here. I'm just going to rewrite it on another page and use the numbers that we've just determined. Okay, so using equation 2 here for the dissociation of uric acid in water, we now are using our concentration of urate ions, which are present at this particular pH and amount of sodium ions. We get 4.9 by 10 to the minus 4 moles per liter. The pH tells us the concentration of hydronium ions, that's 3.98 by 10 to the minus 8 moles per liter. So if we write a Ka expression for this particular weak acid, we have the concentration of urate ions times the H3O plus. We don't include the concentration of water, we assume that's constant, over the concentration of HUR, which is what we're trying to determine here. So that works out to be our Ka expression, our Ka value, which was 3.98 by 10 to the minus 6. And then you want to rearrange that expression so that you get the concentration of HUR is going to be equal to the concentration of UR minus 4.9 by 10 to the minus 4 times the H3O plus, which is 3.98 by 10 to the minus 8, and then divided by the Ka, which is 3.98 by 10 to the minus 6. And that works out to give you an answer of 4.9 by 10 to the minus 6 moles per liter. Now, this number, so this is the amount of uric acid that you have present at pH of 7.4 with a concentration of sodium ions of 0.130 moles per liter. So that's a particular concentration you have of your uric acid. But you're also given in the question a solubility number here, which is very important now. The solubility of uric acid is 5 by 10 to the minus 4 moles per liter. That's basically the maximum amount of uric acid that you can have dissolved in the blood at that particular temperature. So if the number is greater than that, then you get precipitation, and if the number is less than that, then you won't get precipitation. So if we compare our number, which is this, to 5.00 by 10 to the minus 4 moles per liter, we can clearly see that the concentration of HU or uric acid is less than its maximum solubility, so therefore you don't get any precipitation. So there'll be no precipitation. So that's the answer to question 4, part B, part 1. Now we've just answered the question which said that in the first part at pH 7.4, the concentration, so at pH 7.4, the concentration of your uric acid HUR was equal to, let's just get the number again. So I've just written down these numbers here from part 1. So at pH 7.4, concentration of uric acid turned out to be 4.9 by 10 to the minus 6, which was less than its solubility, its maximum solubility of 5 by 10 to the minus 4. So at pH 7.4, you get no precipitation of your uric acid. The uric acid solid. Now these crystals, if they form, they're known as kidney stones because they're made up of crystals of uric acid. So you don't want this stuff forming inside your body, and it seems to be pretty safe at pH 7.4, though they can form if you're taking other medication which disrupts the sodium ion balance. These can form when the concentration of uric acid and urate are high and the pH of urine drops to around 5 to 6. Calculate the pH at which these stones can form. So basically we're talking about a situation where the concentration of HU or uric acid is greater than its solubility, which is greater than 5.00 by 10 to the minus 4 moles per liter. So that's the situation here. Assume that the total concentration of uric acid and urate is 2 by 10 to the minus 3 moles per liter in this particular instance. So we write down our equation of interest again. We're talking about the dissociation of uric acid in water to form urate ions plus hydronium ions. The total concentration we're saying here in this particular instance is 2.00 by 10 to the minus 3 moles per liter. And the solubility of uric acid, we've just said, is right here beside us. So for precipitation to occur, we want to have the concentration of uric acid being greater than 5 by 10 to the minus 4 moles per liter. The total concentration of the two species of question here is 2 by 10 to the minus 3 moles per liter. So therefore, the concentration of urate alone is equal to 2.00 by 10 to the minus 3 minus the 5.00 by 10 to the minus 4, because that's the maximum concentration of acid we need. If we get a concentration above that, then we'll get precipitation. And that gives you an answer of 1.5 by 10 to the minus 3 moles per liter for your concentration of urate. We can write our Ka expression then to work out the pH that we need to get this value greater than 5 by 10 to the minus 4. So Ka equals concentration of urate times concentration of H3O plus over the concentration of HUR. The Ka was from part 1 there, which was 3.98 by 10 to the minus 6. And we just scroll down a bit. That gives you the concentration of HUR we're using as this here, and the concentration of UR we just found. So that gives us a H3O plus concentration of 1.32 by 10 to the minus 6 moles per liter, which is a pH of 5.9. And so the question was calculate the pH at which these stones can form, so the pH value is 5.9. Another way to do this is to use your Henderson-Hasselbalch equation, which relates pH to pKa of the weak acid. According to this equation, log of, in this case, the basic species, which is the urate concentration, over the acidic species, which is the uric acid. And that would be pH is equal to 5.4, which was given to you in the question, the pKa for the uric acid, plus log to the base 10 of the concentration of urate, which we said was 1.5 by 10 to the minus 3 over 5 by 10 to the minus 4, which gives you a pH of 5.9. So again, that's the pH you need in order to get precipitation of the uric acid out of solution and then the formation of these painful kidney stones. So that's the answer for part B, and quite a tricky question. The aqueous system questions can be quite tricky, but if you write down equations, work out Ka values and Ks values where you can, then you're going to pick up marks.